We continued chapter 3 with inverse trigonometric functions, section 3.5. So this should be first a review of material from trigonometry, and that's specifically the definitions of inverse trigonometric functions. And what we'll end up arriving at is the derivatives of inverse trigonometric functions and how to find those derivatives. So just like the previous section or two sections, or a few sections before this, we talked about inverse functions and their derivatives. A way of going about finding the derivatives of an inverse function will be through setting y equal to that inverse function, and then using the definition of one, say like sine inverse of x equals y, using that it's equivalent to or defined as sine of y is equal to x. Okay, and we'll see what we'll do with that in terms of finding derivatives later on for these functions. Remember that these are equivalences. This is essentially how these things are defined, these inverse trig functions right here. Same for the bottom three here. Notice there are two conditions for cosecant inverse and secant inverse. That's that the magnitude of x is greater than or equal to 1. And that's to make sure that we pick only sections of these functions that are 1-to-1, right? So remember that something like x equals sine of y, or the function sine of anything really, is a sinusoidal wave, and it fails the horizontal line test. But if we restrict its domain from negative pi over 2 to pi over 2, then we have a monotonic function, or a strictly increasing function, or a 1-to-1 function is really the term that we've used, 1-to-1. So this section of y equals sine of x, or x equals sine of y to be more specific, for this interval, negative pi over 2 to pi over 2, if you look at it on a graph, or if you graph it by hand, you'll see that it does pass the horizontal line test, and it means that that section of the function does have an inverse. So we have to remember that these values are restricted to these intervals. So just like y is restricted to negative pi over 2 to pi over 2, well, we can only plug in values from negative 1 to 1 for the x values in this sine inverse of x function, because if we look over here, well, the only x values we can get out of sine, the only return values here on the right, are between negative 1 and 1, and that's because of the range of sine. So this sort of, all of that is implicit in this restriction on y right here. So nonetheless, each of these line by line has a similar restriction and sort of dealing with the domain and range of each function. We should be a little bit more interested in how we come about finding these derivatives and how to deal with these inverse trigonometric functions in more practical settings. But it is important to remember the domains of these after we get the hang of working with these functions. So we've got a list of all these derivatives. This is convenient to use in the future. It's also in the textbook. We're going to derive one or two of these so that way we actually understand how we got to such a derivative. And the way we do that will look very familiar. And we'll just have to do a little bit of right triangle trigonometry in order to clean up some of the expressions we arrive at. So let's move on and have some, more or less a trigonometric review of these situations. So find the exact value of each expression. So this is going all the way back to trig, right? So we've got secant inverse of 2 is the expression we're trying to find the value of. And it's helpful if we're dealing with an inverse function to say, okay, that has some output value of y, and y is the thing I'm trying to find. So this is equivalent to the secant of y is equal to 2, right? Or 2 equals secant y, as we have here. We've taken the secant of both sides of this equation, and we've arrived at the one on the right by the cancellation property of inverse functions. So now what we're looking for is a value y for which secant's output is 2. And if that doesn't quite clearly do it for us, we could always switch secant over to be 1 over cosine y. So that's how it's defined. So if we do that, we're saying that 1 over cosine y is equal to 2. And then we might be able to do a little algebra here, take the reciprocal of both sides, so 1/2 is equal to cosine y. And now we've arrived at a place where we can actually more easily evaluate this and say, okay, what angle or what value do I plug into cosine to get 1/2? And we just recall that that's the angle pi over 3. So y is equal to pi over 3. Secant inverse of 2 is pi over 3. So let's look again. Does that meet up with the domain that we're talking about? Well, for one thing, the domain or the x value that we got out of this. So this was, oh, sorry, that's that. We're not interested in that. We're interested in what we got as the output here for this y value. These y values need to be between 0 and pi over 2 and pi and 3 pi over 2. Well, pi over 3 is an angle in the first quadrant, so we're in this first interval here. So 0 to pi over 2. So that's an important thing to remember about that. Pi over 3 is between 0 and pi over 2. So there we have it. So now, sine inverse of sine of 7 pi over 3. Now, we're likely to make a mistake here, and this is part of why we're taking a moment to review this from Pre-Calc 2 or a trigonometry course. We're likely to think, oh, sine inverse of sine should just cancel and leave me with 7 pi over 3. Now, the problem we have to consider is, well, 7 pi over 3, that angle is the output of this sine inverse function here. So that y value needs to be between negative pi over 2 and pi over 2. Well, unfortunately, 7 pi over 3 is larger than pi over 2, so that's not a correct value. That's not the output of sine inverse. So we need to be a little bit more careful about this. So the way to go about it is to realize that, well, the sine of 7 pi over 3, the sine of 7 pi over 3 here, we'll let y be equal to that. So that way we can take this whole expression under this bracket here, or above the bracket there, and just write it as sine inverse of y. So it's the sine inverse here of the argument is y, which is sine of 7 pi over 3. And now we'll just consider what sine of 7 pi over 3 is. And what we have to recall is that sine of 7 pi over 3 is coterminal with the angle pi over 3. Remember, we could just take 7 pi over 3 and subtract 2 pi from it, which that is 7 pi over 3 minus 6 pi over 3 to get a common denominator, and we get pi over 3. So it's coterminal because when we subtracted 2 pi from this angle, we arrived at this other angle. They're apart by 2 pi, so they're full rotation away from each other, and we can swap out 7 pi over 3 inside sine with pi over 3. And sine of pi over 3, we just remember from our common angles, is root 3 over 2. Now we know what to plug in for our y value here. And notice, though, there's a shortcut. We'll come back to that. There's an asterisk on the page for that. So sine inverse of y is sine inverse of root 3 over 2. And it's really just this game backwards. What value do I plug into sine to get root 3 over 2? And that's pi over 3. So this feels like we did some things backwards. And notice that when we got to this point down here, we could have just taken a shortcut and realized, okay, well, sine inverse of sine of this, as long as I find the angle that's coterminal to this one and is between negative pi over 2 and pi over 2, which pi over 3 is, well, then I know that my answer, I can just cancel this sine inverse and sine out and write that coterminal angle between negative pi over 2 and pi over 2. But nonetheless, we worked out all the details to get all the way to here. It's good practice. It's good to see how all these things connect together. Okay, tangent of sine inverse of x. So this one does not have a number, but they ask us to simplify this expression. So what we'll do is the same game we played before. Let's take the inner argument and we'll just call it something. Sine inverse of x. Well, let's say that that's y. So we're taking tangent of y is what we're really looking for. And we'll come back to that when we're done. But first, I start with this. I replace the inside with a y there, and now I need to work on this inside expression. So y equals sine inverse of x. Well, that means sine of y is equal to x. And since we're talking about a trig function, it's a good idea to say sine of y is equal to x over 1. Right? Write it as a ratio, because x is the opposite and this 1 is the hypotenuse. And that suggests there's a triangle involving the angle y, opposite side length x, and hypotenuse 1. And that's how these trig functions are defined, after all, in a trig course. So here's y, the angle in a right triangle, one of the angles in a right triangle. The opposite is x. Hypotenuse is 1. And to find the adjacent side, we just need to do the square root of this squared minus this squared And that's this, root 1 minus x squared. Remember, that's from the Pythagorean theorem. You could work that out on your own. Maybe you called this some unknown variable c down here, and then solve for c as a function of 1 and x there, the other two sides. So nonetheless, we fully developed this triangle. And that's one of the main tasks in these types of problems. Because once we have it fully developed, we know all three side lengths, we're able to calculate from this tangent of y, or tangent of sine inverse of x, is the tangent of y, right? That's what we called sine inverse of x. So tangent of y is only a matter of going to this triangle and saying, well, tangent is opposite x over adjacent root 1 minus x squared. And there we have our answer off to the right. So x over square root 1 minus x squared. Now this is somewhat complicated, right? But it's essentially the same triangle every time. Maybe the variables are a little different, the expressions could be different, but the whole method is the same, right? We're going to form this triangle by first making this, giving sine inverse a handle, or whatever inverse trig function we're dealing with, giving it a handle, or a label like y equals that value, and then rewriting that inverse statement in terms of what it means, and then building the associated triangle with that. So let's show or demonstrate the derivative of sine inverse of x with respect to x. Okay, this will be dy dx. Eventually, we'll see why that comes about, but we want to take the derivative of this function. So the thought is to say, well, I'm not sure exactly what I should do here. So what I'll do is I'll say that y is equal to sine inverse of x, right? This is how we handled inverse functions before. So I leave the whole derivative problem for just a moment and say, okay, y equals sine inverse of x. Now I form an equation. I take sine at both sides, or I rewrite what the upper line means, right? So that I can get the second line here. So sine of y equals x. So now I take the derivative with respect to x of both sides of this equation. On the right-hand side, the derivative of x with respect to x is just 1, so that's easy. Now on the left-hand side, the derivative of sine, the outer function, is cosine of y, the inner function, but then times y, the derivative of the inner function, which is just y, so times the derivative of y is y prime. So it's just implicit differentiation. So the derivative of sine y with respect to x is cosine y times y prime. To solve for y prime here, we divide by cosine of y, and we've got y prime equals 1 over cosine y. But now we're kind of stuck, right? We haven't really done this work yet, but we're here. We realize, okay, I need to figure out what cosine of y is, and I know that y is related to x in this way or this way, but the easier or the more useful piece of information is this one, because we know that this side is x over 1, right, as a ratio. So sine of y is x over 1 here. So opposite over hypotenuse, and we have this same triangle, opposite x, hypotenuse 1. We solve for this side, we'll get root 1 minus x squared, and the angle in the middle here, or between the between the hypotenuse and the adjacent side, is y. And now I know if I'm looking for cosine of y, well, it's the adjacent over the hypotenuse here. So then 1 over cosine y is the reciprocal of cosine y, right? So this flips to become this value. So then at the very bottom, we say that y prime, which is dy dx, the thing we were looking for all along, or the derivative of y with respect to x of this function. Well, we have that all the way down at the bottom. Y prime is equal to 1 over square root of 1 minus x squared. If we go back, well, we don't have to go back because that's actually on the page. They asked us to prove this, and there it is. We've arrived at this value, derived this this derivative formula. Okay, so next up, compute the derivative of each of the given functions. So we've got y equals tangent inverse of x, quantity squared. So a chain rule, 2 comes down, times the inner function is tangent inverse of x, and then times the derivative of that inner function, tangent inverse of x. Okay, so now we need to go find our arctangent or inverse tangent derivative. And if I look back on the previous page, I find it right here. And there it is. That thing's derivative is 1 over 1 plus x squared. So just like we did in the problem before, we could have proved that, but we've already done one of those, and they're basically all done the same way. But nonetheless, we're able to use this differentiation rule from the front page there, first page, and we write it as this. This answer is fine. Maybe we write it in ratio in this manner to simplify it a little bit. Either one of those is okay on an exam, so that's fine. We'll move along. Again, remember, we could come up with the formula for this one by doing very similar work to what's up here. Okay, so the derivative of cosine inverse of sine inverse of t. So this is a little bit messier. All right, so we have an outer function, cosine inverse. We'll take the derivative of the outer function applied to the inner function. So cosine inverse's derivative is what? Let's go back and look. It's negative 1 over root 1 minus x squared. Now notice this matches this x. Okay, whatever the argument here is for cosine inverse, we're going to plug in right here for that x right there and square it. Okay, so let's go back and see what happens in that first step. So yes, negative 1 over square root 1 minus the argument, which is sine inverse of t squared. Okay, so let me just show that cleanly. There's cosine inverse's argument. It doesn't matter what that function is. We picked it up just like it was an x, and we placed it right here where we're squaring that x in the formula. Just place it right into it, and that's just fine. We'll leave it as is. Remember, though, that there's a chain rule, and it's the derivative it's times the derivative of this function, and that's exactly what we see to the right. So d dt of sine inverse of t. And this one's easier. We actually have it on the page. Look up at the top and realize, okay, this one's derivative is 1 over root 1 minus t squared in this case. And since that's 1 over, we just put it, and it's times the preceding function, we just put it all underneath the same numerator. But this could have very well been this fraction times 1 over this expression here. Nonetheless, this is the same value as that. So it's not too bad. Remember, we can use, we can nest these functions, and we can use the chain rule whenever that comes up, and we should use the chain rule whenever that comes up, just to be careful with all this. So lastly, we'll look at a couple of limits involving inverse trig functions, and the most important limits in this section really are arctangent and the inverse tangent, right? So as x goes to infinity, tangent inverse of x is equal to pi, or the limit of tangent inverse of x is equal to pi over 2, or tangent inverse of x approaches pi over 2. If we go to negative infinity, tangent inverse of x approaches negative pi over 2. So those are two nice limits there. You can look at a graph of y equals tangent inverse, or y equals arctangent of x, and you can confirm that both of these two limits are visually implied by that graph. Okay, so they ask us here to find each limit. So if you deal with inverse trig functions and limits, usually we just kind of want to use all the same rules we used before. These inverse trig functions are continuous, just like trig functions. So we can pass the limit through. So the first way I'll solve this is to use that continuity. The limit of arc cosine is arc cosine of the limit, right? So I've switched their places. As long as this limit here exists, and as long as that value is defined in arc cosine's argument, right? As long as it's in the domain of arc cosine. So those are the two conditions. The limit exists as a real number, and also arc cosine is defined for that value. So let's see how this pans out. So the limit as x goes to infinity of this expression, well, we look at the lead terms. X squared has a coefficient of 1 in the numerator. 2x squared, 2 in the denominator, so 1 over 2 is what this approaches as x approaches infinity. So this is really equal to arc cosine of 1/2. Well, 1/2 is between -1 and 1. That's the domain of arc cosine. So this is well defined for arc cosine. So arc cosine of 1/2 is just pi over 3. In other words, what angle do we take the cosine of to get 1/2? And that's pi over 3. The other way to do this is maybe a substitution. You say, well, u is equal to this big clunky expression in arc cosine's argument. And so what happens to u as x goes to infinity? So we could write it out like this. The limit as x goes to infinity of u is, well, the limit as x goes to infinity of this expression. And we just did that analysis. We see that that's 1/2. So then we can just write down, okay, limit as x goes to infinity of this function u is 1/2. And then I can ask, okay, overall, my original limit was this, and this I can switch because I know that as x goes to infinity, this goes to 1/2. So I can swap all of that rational expression out, rational function out for the letter u, or the variable u, let u approach 1/2, pop that into here, and then I'm just doing this as the arc cosine of 1/2. And that doesn't necessarily use the continuity of arc cosine, or I guess it actually does. In the end, we just evaluate it because as long as this 1/2 is in the domain of arc cosine, then it's we can just plug the number in to that inverse trig function. So those are two ways to do this. I think the top is maybe the slightly better way. But if this isn't defined or it doesn't fit into the domain of this function, well then you might have to do more work outside like this. Okay, so lastly, the limit as x approaches 2 from the right of arc tangent of 1 over x minus 2. So 2 from the right, I can't just plug 2 into this because I get 2 minus 2 in the denominator, so that would be undefined, so I have to be careful. As x approaches 2 from the right, these are values like 2.1, 2.01, 2.001. Those numbers minus 2 are all positive. So we have x minus 2 is approaching 0 from the right, so positively, and 1 over 0, well, 1 over something approaching 0 is approaching infinity. So this is approaching positive infinity. So this is all written right here. The limit as x approaches 2 from the right is equal to the limit, or sorry, of u, if we make this substitution, well, that's this expression, and that's equal to positive infinity. So now what I could say is this: as x approaches 2 from the right, u approaches positive infinity. And that's what I'll write over here. So as x, so I can swap out 1 over x minus 2, since that's equal to u. And I know that as x approaches 2 from the right, u approaches infinity. So now I'm taking the limit of a slightly simplified function, right? Arctangent of u now. U is going to infinity. Well, this matches exactly what we see above here. X is going to infinity. The limit of arctangent of something going to infinity is pi over 2. And we're able to conclude that that's the case. So these will take a little bit of practice. It's a little bit harder to wrap your head around inverse trig functions. Typically, arctangent is the more commonly seen function for this. It's going to come up a lot in Calc 2. You'll see this function come around again. We'll do it quite a bit of it in Calc 1 still as well. The other inverse trig functions are a little bit easier to manage. They don't have quite an interesting infinite derivative as arctangent does.